Okay, so let's give you the example of 1 over s. So it is 1 over j omega, which can be converted to minus j over omega. Now the magnitude of this thing, it will be 1 over omega, right? J, well, j has no magnitude. It is just in the complex plane, it's just 1 over omega pointing downwards. And its phase is 90 degrees. When omega is 1, magnitude is 1, as you see. And its logarithm, or the dV magnitude, will be 20 times log of 1, which will be 0 dBs. Okay. So you are going to have the following. I'm just plotting the magnitude now. Let's say this is omega. Let's say this is 1. And let's say that this is 0 dBs. This is where you have your 1 point in your magnitude plot. This is the dB plot, let's say. Now, what is the slope of that magnitude going to be? As we said, it is going to be minus 1 as omega goes down. So it will be, in terms of dB, it will be minus 20 dBs. It will be like this. Slope will be minus 20 dBs. And since this is a logarithmic plot, this will be per the so-called decade, which means the following. If this is 0.1, if this is 10, at 0.1, you will be at 20 dBs. At 10, you will be at minus 20 dBs, etc. It will be a straight line like this. Okay. This will be the plot of a integrator, 1 over s squared. I hope this is a little bit clearer. Yes.
I'm sorry to interrupt you, but I think I missed the part. We write j over omega instead of 1 over j omega.
This one?
So we just multiply it by 1 over j omega. Is it the case?
Well, no, 1 over j omega, we multiply it by j.
Okay, Jamais.
This is standard, so I didn't want to spend time on this. So, for 1 over s, this is what we have. For 1 over s squared, you have, this is 1 over s, and this is 1 over s squared, let's say. Something like this. This is so whose slope is minus 40 dBs per. So, and the phases are minus 90 degrees. Okay. So let's go to our third thing, which is, let's say, j omega t plus 1. Let's say G3 is this one. Okay, let's not write it like this. We will analyze this thing in two components. As you know, j omega t1 plus 1. This is actually a complex number like this. This is the real part. This is the imaginary part. This is the real part is 1. The imaginary part is omega T1. Right? So that this number is this combination of these. This is G3 as a complex number. Now we will look at the extreme cases, the so-called asymptotes. When, for example, omega times t is much less than 1, okay? So this term is much, much smaller. This term here, this one, will be negligible compared to the other one. So j omega t1 plus 1 can be approximated by 1 because this term is negligible, okay, compared to the other one. You are somewhere around here, let's say, so that you're on one side. On the other hand, omega t, when it is much greater than 1, you can write j omega t plus 1, t1 plus 1, approximately as j omega t1, let's say. Actually, I don't know why I'm keeping this one thing. Actually, it's not even necessary. I can just delete this one. This one. Omega t is enough because I'm not going to use a second t anyway. So omega t. So for very low frequencies, omega goes to 0, and here omega goes to infinity. For very low frequencies, it is equal to 1. For very high frequencies, it is equal to j omega t, what you have. We have actually, we have analyzed these cases. This is a constant gain, and this is a term like S times T. So we have analyzed that also. So actually, we know what kind of things they are. If I try to plot it like a G, at the let's say this is 0. Since it is 1, the logarithm, the decibel of that is 0 dBs. So at very low frequencies, you are here. And there is this at very high frequencies, you have slope equals, let's say, +1 or 20 dB per decade here. So you are somewhere around here for very high frequencies. And for very low frequencies, you are here, very high frequencies, you are there. In between, you will be somewhere in between, okay? Here you have omega t equals 1 or omega equals 1 over t. You have the so-called break point. And there, as you see, this j omega t starts acting like a differentiator. So the real thing is going to be something, these are the asymptotes, and will be something like this. This will be j omega t plus 1 magnitude.
Is it going to be parabolic?
I don't know, probably not. Probably not. No, this is, but it is going to be, deviating from, it is exactly these values at the high and low ends, but it is going to be,
So, I mean, is the graph touching the VT equals 1 point? Because it is like, it's not
no, it
going to
doesn't
the...
touch. There is a difference here.
Okay, I see.
And for the phase angle, when omega t is much smaller than 1, again, you have the phase angle of 1 is 90 degrees, as you know. Sorry, 0 degrees. What is 90 degrees? And when omega t is much greater than 1, the phase angle of j omega capital T, the phase angle of j is 90 degrees. And when omega t is equal to 1 exactly, the angle of j omega t plus 1, it is 1 plus 1, so this will be 45 degrees. Okay. So if I plot the phase now, you start from 0 degrees. This is, let's say, 90 degrees. This is 55 degrees. So this is omega t equals 1. You will have something like this. You will start from 0. Pass from this point on, and then come to the 90 degrees. So this will be the more or less the phase of your j omega t equals 1. Okay. So this will be this is the magnitude plot, and this will be the phase plot.
Hocam, isn't our base form includes sine waves, like sine something, sine omega t plus phi we wrote in the beginning. So like, how do we get a like almost linear graph in the upper part, the
magnitude part?
Yes, the magnitude.
This is the magnitude as omega changes. This is how the magnitude changes as omega changes. Okay. This is especially for one case only. What do you mean we get a linear graph? This is the ratio of the input amplitude to output amplitude, or output to input. I know that these concepts are, they are hard. I'm throwing too many things at the same time to you, but that's how this course is. I'm sorry about that. I know that it's very difficult to understand it, especially at the end of the semester.
Yes. I mean, like in the beginning, we draw like UT and YT graphs, and we define the TY and the phase angle between them. We draw the steady state and transient part. Didn't we draw it according to magnitude of the frequency response?
Yes, and so this is the magnitude of the frequency response.
We draw them oscillatory, but like
No, don't mix them up. These are we are talking about different things here. Now,
okay.
Input to a system, let's say, is sinusoidal. Okay, this is input. Output is sinusoidal of the same frequency. Input has an amplitude U0. Output has an amplitude of Y0. Now, Y0 over U0, their ratio is the amplitude of the transfer function. Okay. Now, this thing, this G of J omega, we plot it as we change this omega frequency, and we find that it is, I don't know, something like starts from here, goes here, then stays here, goes up, etc. Whatever. Goes down even more. So this is how this frequency response magnitude changes as the frequency omega changes. Okay? So at a different omega, let's say a faster omega, this is omega goes up, let's say, you will have a different kind of response like this. And you will just plot, one is here, the other is there. You plot, each of these are plotted here. I don't know. Do you understand? Kind of?
Yeah, kind of, hocam. I see. I get they are different things.
Yeah, there are different things. So, okay, let's skip this part. So what were we doing? We were talking about j omega t plus 1. Well, let's say that we said 3. Well, let's say that this is 3a is this one. Now we will go to the other part of 3. That will be, let's call it 3b, which is 1 over j omega t plus 1, because this is important. What shall we have here? We will have, again, we will look at the asymptotes, okay? When omega t is much less than 1, we have, this term is negligible, so the magnitude of g is approximately 1. When omega t is much greater than 1, you have what will that be? 1 over omega t, I suppose. Okay. Yeah. Which means that it will be going to 0. So, and you can take the logarithms of these and find decibels, etc., etc. And for the phase, omega t, for small frequencies, phi is equal to 0 degrees. Omega t is much greater than 1. You have phi is equal to minus 90 degrees here. And when omega t is 45, sorry, omega t is 1, phi is minus 45 degrees. So the plots are going to be as follows. So this is the dB plot. Omega. we start from 0 dBs. This is omega t equals 1, or omega equals 1 over capital T, which is the break point. Okay. So it goes on like this. And then there is the break point in which the slope is minus 20 dB per decade. And the plot is, the real plot is something like this. Okay. It starts from 0 dBs and goes down. And this difference, the difference is the maximum at this point, and I think that was 3 dBs or something, if I'm not wrong. So this is the magnitude plot. The phase plot looks like the following. Zero. Well, actually, let me just show this to you using some examples. I think this was too complicated. So let me try to use some MATLAB-like thing to show you these at least, so that you will have a better idea. Okay. What is it? Okay, let's define, for example, G as the transfer function of 1 and let's say 5 and 1. So it's 5s plus 1, okay? This is the system. So if we say the border plot of this G, let's see what we will get. This is more or less very similar to what I have drawn here, as you see. It starts from 0 dBs, okay? And then there is a break point. The break point is the point at which these lines intersect, the asymptotes intersect somewhere around here, I think, probably here. Our example was, well, what was it? It was G of S was 1 over 5s plus 1, 5 plus 1 plus 1. Yes. So G of j omega here is 1 over j 5 plus 1. So omega equals is the breakpoint. And if we look at it here in our figure, you start from 10 to the minus 1. I cannot draw here, can I? No. But here is your breakpoint. Here is your breakpoint. Okay. And at that breakpoint, the frequency, the phase angle is exactly 45 degrees, as you see. This phase angle starts from 0 degrees, goes to minus 90 degrees, as you see. So this is the Bode diagram of a first order system, as you see. Okay. Okay. If I draw the Bode diagram of a, let's say, an integrator or something, let's say 1, 0, 1 over S. Let's plot this Bode diagram of this one so that you believe me. This is what we have. This is the Bode diagram of 1 over S. It has a slope of 20 decibels per decade. Decade means from 10 to the 0 to 10 to the 1, the magnitude in decibels drops 20 dBs from 0 to minus 20. In another decade, 10 to the 1 to 10 to the 2, let's say, it drops another, let's say, 20 decibels, etc. And its phase is minus 90 degrees all throughout. Now, if I combine, for example, these two things I have done before, if I plot the Bode plot of that, I'll come to that, but we will get a combination of those Bode plots. How we combine them, I will explain them. Probably not today, but with an example the next time. So it is possible to combine them. The important thing is the software combines it for you actually, but you should be able to interpret the software where, for example, what kind of transfer function, well, gives you this response, for example. You should be able to understand that. Okay, so let's go back to our thing. So we looked at a simple gain. We looked at an integrator or a differentiator. Then we looked at first order systems. Let's look at the last example, which will be 1 over, as we have said, j omega over omega n plus 2 omega j omega over omega n plus 1. Okay, let's look at this thing, this example. Again, we will be looking at the asymptotes, and omega is much less than omega n. So when omega is close to 0, omega is much less than omega n means that these terms are very small. So you have the amplitude is equal to 1, okay? And G in terms of dBs will be equal to 0 dBs, okay? Which will be 20 times log of 1 will be 0. On the other hand, when omega is much greater than omega n.
Hocam,
Yes.
the j omega over wn term is squared, right?
Squared, yes. Yeah.
Thank you.
When this is the case, so this term is omega over omega n is very large. Its square is even larger now. Actually, you are going to have the magnitude. The other terms can be neglected here. The magnitude can be written as omega over omega n to the power minus 2, right? That is 1 over omega n squared. And its slope is going to be, well, it will be, or you can even say j omega over omega n to the minus 2. So it has a slope is equal to minus 2 or minus 2, or let's say minus 40 dB per decade. Okay. Well, this is a second order system, so we know that it has resonances and so on. But let me plot it to you. One more thing, g of j omega when omega equals omega n. What do we have here? You can find that. It's not too hard to find that. This will be equal to 1 over 2 times the zeta, okay? The magnitude when omega is equal to omega n is what we will have here. So, if we plot the magnitude, this is omega, let's say this is in terms of dBs, you start from 0 dBs, and then let's say this is where omega is equal to omega n, the so-called frequency that is close to resonance. So you have an asymptote here, and you have an asymptote that has a slope of minus 2. Minus 40 dB. Okay. So you will get a family of curves like this. I cannot draw it very well. Let me try to. Yeah, something like this. Depending on the value of zeta, you will get different curves. So even if you have even less zeta, this is what you are going to have actually. A kind of resonance-like thing. Eventually, all these curves are going to end up at this high frequency thing. This is the magnitude, which you know from the resonating systems. And for the phase, you start from this omega equals omega n. You have a phase angle that, again, as a function of zeta, you have the following phase angle term. For very low zeta, you have the following curve. And then as zeta increases, you have smoother curves. Why did I use this? Okay. And the phase starts from 0 degrees and ends up at 100 minus 108 degrees. And also,
Hocam, so in this case, what do we want zeta to be, hocam? Low or high?
well, usually you don't get to choose. This is, the damping ratio is a property of the system. Well, if you have a control system, you can choose whatever damping ratio you want to select. But if you have a physical system like a spring damper mass, the damping in the system dictates the damping ratio. If you can choose, it depends on your application. In control systems, you probably want the damping ratio to be kind of high, like around 0.7, 0.8 or something, even close to 1, because that gives very little oscillation. But if you have a mass spring damper system, you don't get to choose your zeta. It is determined by the damping. Okay.
I got it, hocam. Thank you so much.
All right. So I guess I'll have to stop here. There is one more thing which, let me just talk very briefly about it. The fifth one is e to the minus SD corresponds to e to the minus j omega d, which you can write it as cosine omega d minus j sine omega d. This is, as I said, is the time delay that is seen in certain systems. Now, this thing has a sorry, I should say j omega d.
Hocam, what is D?
D is the delay, how much delay there is. Okay.
So it is given, right?
Yes, it is given. But this will be 1 because it's cosine squared plus sine squared. And the phase angle of e to the minus j omega d is going to be, I think, it is simply minus omega d. So the gain is 1. Gain is 1 or 0 dB. Phase is minus omega d. So it increases linearly with omega. As I said, time delay is important for in chemical processes, not much in well, we don't get to use that much in mechanical engineering, but in chemical engineering, for example, it's quite important. Anyway, the next time we are going to try to plot a large transfer function. But before that, again, let me go and let's do a second order system, a very simple second order system, so that we plot the border of V. Well, you see that this is a second order system with a little bit of resonance, but let's increase this so that this will be, let's decrease the damping so that the resonance will be clearer. Okay, so this is what we get in the border diagram. As you see, it goes up and then it goes down. The slope here is minus 40 dB per decade, and this is the phase, starts from 0, goes to 180 dB of a second order system. This is a little bit different from what we have seen in 301, because in 301 we were plotting not the logarithmic but linear omega plots. So logarithmic plots are a little bit different, but the shape is more or less similar.
Hocam, so we need to increase the n value in order to like hocam, bu çizdiğiniz artık ucu gözükmeyecek şekilde sonsuza gidiyor sanırım orada. Şeyi sağlamak için desibel frequency graph'ta. Hocam, bir slide yazdığınız yerde yukarı çıkabilirsiniz. Şurada low zeta dediğiniz aşağıda hocam.
Bu mu?
En son çizdiğimiz grafikte hocam. Desibel grafiğinde, desibel frequency grafiğinde. Burada hocam low zeta dediğiniz yerde artık bir yerden sonra sonsuza gidiyormuş gibi çizdik ya o kısımda. Onun için n'i düşürmemiz lazım değil mi? Çünkü slope n'e bağlı.
Hayır, ama bu ikinci dereceden sistem, bunu n'i değiştiremeyiz yani. Zeta 0 olsaydı mesela bu şöyle olacaktı. Bu tam böyle gelecek. Burada zıp diye şöyle bir şey olacaktı.
Yok sol taraf için konuşmuştum hocam.
Sol taraf burada. Zeta 0 olunca burada rezonans var zaten. Sonsuza gidecek yani.
Yani n değerini kendimiz değiştiremeyiz o zaman herhalde değil mi?
Yani hayır. N burada 2 zaten. Yani değiştirecek bir şey yok.
Peki farklı grafikler olmasının sebebi ne hocam? Aslında hepsi bir tane denklem için mi şu an? Yoksa farklı denklemler
Hayır, her
için?
biri farklı denklem için. Mesela bu dördüncü şunun için. 3B bunun için. 3A şunun için vesaire yani.
Anladım. Tamamdır hocam. Teşekkürler.
So,